This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is series parallel voltage divider circuits. Our objective today is to take a close look at series parallel voltage divider circuits in both the unloaded and the loaded condition. Voltage dividers are common series parallel circuit configurations, and this lecture assumes you have a passing familiarity with basic series parallel circuit analysis. If you haven't watched the series parallel DC circuit analysis lecture, available at the Big Bad Tech channel, or only dimly recall its contents, by all means take the time to do so now. As anyone that has ever organized or meticulously planned an event can tell you, no plan survives first contact. This is true for the biggest of battles all the way down to a kid's birthday party. Success, and sometimes survival, means you often have to toss that beautiful plan out the window and deal with the crumbling reality before you. The same is true for a voltage divider circuit in the unloaded and the loaded condition. If you can walk away from this lecture with a simple understanding that you cannot use any data obtained during circuit analysis of a voltage divider in the unloaded condition to solve for those same quantities while in the loaded condition, I will consider my time having not been spent in vain. Voltage dividers in the unloaded condition are totally different circuits than voltage dividers in the loaded condition and must be analyzed as such. Voltage dividers often take the form of a series parallel circuit with one or more switches, as I've illustrated here. If switch 1 is open, the load resistor is effectively removed from consideration, and R1 and R2 are placed in a pure series configuration. As an exercise to the viewer, I invite you to solve for the voltage across and the current through each element in this system while the switch is in the open state. Additionally, see if you can use Kirchhoff's voltage law to determine the voltage at node X with respect to ground, the voltage at node Y with respect to ground, and finally the voltage across the switch, node X to node Y. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. For this pure series circuit, source current equals I1, which equals I2. No current travels through the load. As such, there will be no voltage across the load. A Kirchhoff's voltage law analysis of this circuit suggests that E equals V1 plus V2. Perhaps the easiest way to solve for these unknown properties is to use the voltage divider rule. The voltage divider rule demonstrates that V1 is 1.9 volts. An algebraic manipulation of the Kirchhoff's voltage law equation for this circuit demonstrates that V2 is the remaining 46.1 volts. An application of Ohm's law demonstrates that I2 is 38.4 milliamperes. While switch 1 is in the open state, this is a pure series circuit. As such, source current equals I1, which equals I2, and they all equal 38.4 milliamperes. Nodal voltage Vx is equal to the rise E minus the drop V1. Substituting our given values demonstrates Vx with respect to ground is 46.1 volts. Given switch 1 is in the open state, node Y is also at ground, and as a result, node Y exhibits a 0 volt differential with respect to ground. This means Vxy, the voltage across the switch, is 46.1 volts. Let us now consider the radically different behavior of this same circuit when switch 1 closes. When switch 1 closes, there is another current path in this circuit. As such, we must jettison absolutely everything from our previous pure series circuit analysis and begin anew. With switch 1 closed, a Kirchhoff's current law analysis of the series parallel circuit demonstrates that source current must travel through I1. Source current then splits into two paths, one path leading through R2, the other path leading through the load resistor. As such, the Kirchhoff's current law equation for this circuit is I source equals I1, which equals I2 plus I load. A Kirchhoff's voltage law analysis of this loop in red suggests that E equals V1 plus V2. A Kirchhoff's voltage law analysis of this loop in orange suggests that E equals V1 plus voltage across the load. Finally, a Kirchhoff's voltage law analysis of this loop in yellow suggests that V2 equals the voltage across the load. These analyses imply that R2 is perfectly in parallel with the load resistor. The parallel combination of R2 and R load is 461.5 ohms. Let's call this simplification R single prime. R single prime is perfectly in series with the resistor R1. A Kirchhoff's voltage law analysis of the pure series simplification suggests that E equals V1 plus V single prime. A Kirchhoff's current law analysis demonstrates that source current equals I1, which equals I single prime. There's a couple means of solving for our properties of interest. Perhaps the easiest means of doing so is through use of the voltage divider rule. The voltage divider rule demonstrates that V1 is 4.7 volts. An algebraic manipulation of the Kirchhoff's voltage law equation for the pure series simplification demonstrates that V single prime is the remaining 43.3 volts. An application of Ohm's law demonstrates that I1 is 93.8 milliamperes. We know that source current is also equal to 93.8 milliamperes. Voltage across elements in parallel is the same. V single prime is the parallel combination of R2 and R load resistor. As a result, V single prime equals V2, which equals the voltage across the load, which equals 43.3 volts. An application of Ohm's law demonstrates that I2 is 36.1 milliamperes. Similarly, another application of Ohm's law demonstrates that current through the load resistor is 57.7 milliamperes. As a means of checking our work, you will note that I2 plus I load yields the expected value of 93.8 milliamperes. All current that went in has indeed come out. Ideal switches are 0 ohm elements. As a result, no voltage will be dropped across the switch. As a means of checking our work, voltage at node X with respect to ground is equal to our rise of 48 minus our drop of 4.7 volts, or 43.3 volts. Similarly, voltage at node Y with respect to ground is a 48 volt rise minus a 4.7 volt drop minus the 0 volt drop across the switch for a total of 43.3 volts. Voltage at X with respect to Y, where both are at 43.3 volts, demonstrates there is a 0 volt differential from X with respect to Y. Alright, here's another example of a series parallel voltage divider circuit. Let's do this as a two-part exercise. Part 1, switch open. Part 2, switch closed. Let's check in between part 1 and part 2 to make sure you're tracking. Part 1, switch open. As an exercise to the viewer, I invite you to solve for the voltage across and the current through each element in this system and the voltage across the switch while in the open state. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. While in the open state, a Kirchhoff's voltage law analysis of this circuit suggests that E equals V1 plus V2. A Kirchhoff's current law analysis of this circuit while switch 1 is in the open state suggests that source current equals I1, which equals I2. These analyses imply that R1 and R2 are perfectly in series with one another. As a result, no current will flow through the load resistor and no voltage will be dropped across it. An application of the voltage divider rule demonstrates that V1 is 1.8 volts. An algebraic manipulation of the Kirchhoff's voltage law equation demonstrates that V2 is the remaining 22.2 volts. An application of Ohm's law demonstrates that I2 is 11.1 milliamperes. While in the open state, I source equals I1, which equals I2, and they all equal 11.1 milliamperes. Voltage at node X with respect to ground is the rise E minus the voltage drop V1. Substituting our given values yields 22.2 volts. While the switch is in the open state, node Y exhibits no differential with respect to ground. As such, Vy is 0 volts with respect to ground. Voltage across the switch, node X to node Y, is 22.2 minus 0, or 22.2 volts. Voltage across the switch is 22.2 volts. All of this changes when switch 1 is closed. Part 2, switch closed. As an exercise to the viewer, I invite you to solve for the voltage across and the current through each element in this system and the voltage across the switch while in the closed state. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. While in the closed state, a Kirchhoff's current law analysis of this circuit suggests that source current equals I1, which equals I2 plus I load. A Kirchhoff's voltage law analysis of this loop in red suggests that E equals V1 plus V2. Another Kirchhoff's voltage law analysis of this loop in orange suggests that E equals V1 plus V load. Finally, a Kirchhoff's voltage law analysis of this loop in yellow suggests that V2 equals V load. These analyses imply that R2 is perfectly in parallel with R load, a simplification I'm calling R single prime. The parallel combination of R2 and R load is 625.4 ohms. A Kirchhoff's voltage law analysis of this loop in red with a pure series simplification demonstrates that E equals V1 plus V single prime. A Kirchhoff's current law analysis of the pure series simplification demonstrates that I source equals I1, which equals I single prime. An application of the voltage divider rule demonstrates that V1 is 3.3 volts. An algebraic manipulation of the Kirchhoff's voltage law equation for the pure series simplification demonstrates that V single prime is the remaining 20.7 volts. An application of Ohm's law demonstrates that I1 is 33.1 milliamperes. It can be said that source current equals I1, which equals 33.1 milliamperes. Given R single prime is a parallel combination of R2 and R load, it can be said V single prime equals V2, which equals V load, and they all equal 20.7 volts. Voltage across elements in parallel is the same. An application of Ohm's law demonstrates that I2 is 10.3 milliamperes. Similarly, another application of Ohm's law demonstrates that current through the load resistor is 22.7 milliamperes. As a means of checking our work, I2 plus I load equals 33.1 milliamperes. In the closed state, the 0 ohm switch experiences a 0 volt differential. As such, Vx with respect to Y will be 0 volts. Alright, one last illustrated example before I send you off to bed. Series parallel voltage divider circuits may be thought of as a simplified way of accounting for transmission losses in electrical circuits. Consider two switched DC motors modeled as 18 ohm and 9 ohm resistors, serviced by a 36 volt source. However, the means of transmitting power from the source to the load is modeled as a 500 milliohm resistor, Rx. As an exercise to the viewer, I invite you to solve for the voltage across, the current through, and the power consumed by each load in this system, as well as total power for 3 different scenarios. Scenario 1, switch 1 closed, switch 2 open. Scenario 2, switch 1 open, switch 2 closed. And finally, scenario 3, both switch 1 and switch 2 closed. Note, these 3 scenarios necessitate 3 different analysis sessions, as each scenario presents a unique circuit and must be analyzed as such. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. With only switch 1 closed, it places Rx and R1 perfectly in series with one another. An application of the voltage divider rule demonstrates that V1 is 35 volts. An application of Ohm's law demonstrates that I1 is 1.9 amps. With only switch 1 closed, source current equals I1, which equals Ix, and they all equal 1.9 amps. P1 equals V1 times I1. Substituting our given values demonstrates that P1 is 68.2 watts. Total power is equal to supply voltage times source current. Substituting our given values demonstrates total power is 70.1 watts. This means Px is the remaining 1.9 watts, which might be considered a loss to the system. Part 2, switch 1 open, switch 2 closed. The closure of switch 2 places R2 perfectly in series with Rx. An application of the voltage divider rule demonstrates that V2 is 34.1 volts. An application of Ohm's law demonstrates that I2 is 3.8 amps. With switch 2 closed, this is a pure series circuit, and as such, source current equals I2, which equals Ix, and they all equal 3.8 amps. P2 equals V2 times I2. Substituting our calculated values demonstrates that R2 consumes 129.2 watts of power. Total power equals supply voltage times source current. Substituting our given values yields 136.4 watts, meaning Px is a remaining 7.2 watts, which might be considered a loss to this system. Finally, part 3, switch 1 closed, switch 2 closed. 2 paths for current exist, and R1 is perfectly in parallel with R2. The parallel combination of R1 and R2, a simplification I'm calling R single prime, has a value of 6 ohms. R single prime is perfectly in series with Rx. An application of the voltage divider rule to the simplified series circuit demonstrates that V single prime is 33.2 volts. Given R single prime is a parallel combination of R1 and R2, it can be said V single prime equals V1, which equals V2, and they all equal 33.2 volts. Voltage across elements in parallel is the same. An application of Ohm's law demonstrates that R1 draws 1.8 amps. Another application of Ohm's law demonstrates that R2 draws 3.7 amps. Source current is equal to I1 plus I2. Substituting our calculated values demonstrates that source current is 5.5 amps. P1 equals V1 times I1. Substituting our calculated values demonstrates that R1 consumes 61.3 watts. P2 equals V2 times I2. Substituting our calculated values demonstrates that R2 consumes 122.7 watts. Total power equals supply voltage times source current. Substituting our calculated values demonstrates total power is 199.4 watts, meaning Px is the remaining 15.3 watts, which might be considered a loss to this system. All right, that's about it for today. In conclusion, this lecture took a look at series parallel voltage divider circuits in both the unloaded and the loaded condition. We learned that values obtained during the circuit analysis of the unloaded condition cannot be used to calculate values during the loaded condition because the unloaded and loaded conditions represent radically different circuits and must be approached as such. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.